Okay, so in this video, we're going to be going over two concepts that are famously confused, and those concepts are permutations and combinations. Okay, and I'm going to go over a bunch of examples. Okay, they're going to be simple examples, but hopefully they really illustrate the ideas behind these concepts. And rather than trying to sort of memorize, some sort of situation where you use permutations or you use combinations, I want to try and get you to understand what kind of pattern of thinking you fall in naturally when trying to solve problems, and I want to try and get you to be able to recognize those patterns, and so you don't have to memorize anything. It just sort of makes sense to use either permutations or combinations to solve the problem. So that's the idea. Okay, so the first example, I'm going to start with an example, then give you the definition, so hopefully the definition will make more sense after having seen it in context. So how many four-letter strings can be made using the letters in the set containing W, O, R, and D, each exactly once. Okay, so four-letter strings, most people would call that a word. Okay, but for instance, this is not a word, right? So I'm just calling that a four-letter string. Okay, so we want to figure out how many four-letter strings can be made using the letters in this set, each exactly once. So they're all going to have four letters. There are four letters in the set, so we have to use all of them. Okay, each exactly once. So this is an example of such a four-letter string. That would be another one, and so on. Okay, we want to figure out how many are there. Okay, how many are there? So what we can do is we can kind of put these four slots in which we can put these letters. Okay, and in each slot, I'm going to actually count the number of choices I have for letters to be put in that slot. So I'm going to write number of choices, and we're going to start filling some of this information in. Okay, so for my first letter right here, well, I can use any of the letters in this set. So I could put a W, I could put an O, I could put an R, or I could put a D. Okay, so that's four different choices I have for that slot. Okay, and then for each of those choices, for the second slot, I have three further choices. Okay, so for each of the four options here, I have three options for the next letter, right? Because I have to use each letter exactly once. I already used one of the letters for the first slot. Can't use it again. So for each of those four options, I have three options for the second letter. So how many total choices do I have for the first two letters? Well, you can see I've listed them all. There's 12. How would I get 12 in general? Let's say if it was, an n letter string, and there were n letters in this set, right? I'm just doing the example where n is 4 here. What would it be in general? Well, there would be n options for the first letter, and since I already used one there would be n minus 1 for the second letter. And so the total number of options for the first and the second letter would be n, right? Here n is 4, times n minus 1, right? Because I have four groups of three letters. That's 4 times 3, that's 12. Okay, and in general, it would be n times n minus 1. Okay, so that's the number of options I have for the first two letters. How about for the third letter? Well, for each of these 12 options I've listed here, how many options do I have for the third letter? I have 2, right? No matter which two letters I choose for the first two slots, okay, there's still 2 letters remaining I could choose for the third slot. So that's a total of 4 times 3, that's 12 times 2. And then there's just one letter left at the end for the last slot. Okay, so our answer here is 4 times 3 times 2 times 1. And this quantity, right, multiplying 1 times 2 times 3 times 4, or in general all the way up to some number n, appears so often it gets special notation. So this is 4 with an exclamation point. Okay, so that's called 4 factorial. And I'll just say in general, n factorial is n times n minus 1 times n minus 2 dot 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 all the way times 2 times 1, and this is n factorial. Okay, so that quantity comes up so much, we have that concise notation for it, and that's our answer. Okay, so that's how many 4-letter strings we can make using those letters. I encourage you, if you don't believe it, try writing them all out. You'll see you get 4 factorial, which is 4 times 3 times 2 times 1, which is 24. So there's 24 different 4-letter strings using the letters in that set exactly once. Okay, so that was our first example, and now what we're going to do is actually give a definition, and this definition is for permutations. And you'll see how it lines up with the example in a second. So a permutation is a linear ordering of the elements of a set. Okay, so you can see up here that's actually what we were counting in the first question. We were just counting the number of permutations of the elements in this set, right? Why was it a linear ordering? Well, it's because we were looking at 4-letter strings. It mattered the order in which we listed the letters. This is a different 4-letter string than this, even though they both use the same 4 letters. Okay, so we cared about the order in which we wrote the letters, and that leads us to this definition of a permutation, to linear ordering of the elements of a set. We put them in line, we put them in some order, and that's a permutation. There's another definition related called a k-permutation. Okay, k-permutation, and that's very similar. It's just a linear ordering of not all the elements of a set like a permutation, but just of k elements of a set. Okay, so if I have a set containing like 10 different elements, and I want to count how many different ways are there to arrange 3 of those elements in some order, okay, that would be a k-permutation. I would be counting the 3 permutations in that example. Okay, so let's see an actual example to try and get used to this k-permutation definition. So how many sequences of 5 cards can be drawn without replacement, and I'll explain what that means in a second, without replacement from a standard deck of 52 cards. Okay. Okay, so we have a standard deck of 52 cards. For those of you who have never used a deck of cards, I encourage you to go get one, play around with it. There's a lot of things you can do with a deck of cards. Games, magic tricks. Okay, so you have a standard deck of 52 cards. There are 4 suits, hearts, diamonds, clubs, and spades, and each suit has 13 different cards in it. Okay, there's ace, 2, 3, 4, all the way through 10, and then jack, queen, king. Okay, so 13 cards in a suit, 4 suits, that gives you 52. They're all unique. Okay, and we're asking how many sequences of 5 cards can be drawn without replacement from such a deck. Okay, what does without replacement mean? It means when we draw a card, we don't put it back before we draw our second card. Okay, we just keep drawing cards from the deck. Once we draw the first card, there's only 51 cards left in the deck, right? And we keep drawing. Okay, so the 5 cards we get in such a procedure are all going to be different, and we're asking how many different sequences of 5 cards can be drawn. Okay, and that word sequence is telling us we care about the order in which we draw them, right? If I draw the queen of diamonds first and then the jack of clubs second, right, that would be different than drawing the jack of clubs first and the queen of diamonds second. Okay, so we care about the order in which we draw these cards. Okay, so let's do a similar thing to the first example. I'll kind of put my 5 slots here for the 5 cards I'm going to draw, and I'm going to write the number of choices I have at each stage. Okay, so for the first card, of course, there's 52 cards in the deck, so there are 52 different cards I could draw first. And then for each of those cards I drew, okay, when I draw my second card, there are only 51 options remaining. Okay, so how many different choices are there for the first two cards I could draw? Well, there's 52 for the second, and for the first one, and for each of those, there's 51 choices for the second card. So in total, just like we saw up here, right? Just like we saw here, in total we would get, here we got 4 times 3, here we get 52 times 51. Okay, because for each of these choices, there's this many choices for the second card. So that's just adding up 51 52 times, and that's just 51 times 52. Okay, and then for each of these two choices, we kind of keep stringing it along. Okay, there's only 50 cards remaining for the third, then 49, and then 48. So that's our answer. Okay, so that's some big number, but we want to try and write this somehow using our factorial definition because it's starting to look like a factorial, right? What's the only difference? The only difference is that this product, if I wanted to write it as 52 factorial, what's it missing? Well, it's missing times 47 times 46 times 45 and so on. It's missing 47 factorial, right? All of this is actually 52 factorial because this accounts for multiplying 1 through 47, and this is what I need to get to 52. Okay, so if I just multiply and divide by 47 factorial, I haven't changed anything, and that allows me to write this as 52 factorial over 47 factorial. Right, because this is this product times 47 factorial, so I just have to divide by that as well. Okay, but if we look at the top of the page, okay, we can understand what this problem was really asking using our new definition. Okay, this isn't a permutation of the elements in the deck, because that would mean I rearranged all of the 52 cards, but it is a K permutation. What's K here? Well, we're just asking how many different linear orderings of 5 elements from our set of 52 cards you can make. Okay, so let me just write that. So this is just the number of 5 permutations of the set of 52 cards. All right, that's exactly what our K permutation definition was. Okay, so it fits perfectly into that definition. Okay, and so you might be asking yourself, how can we generalize this? Okay, I'll make a note. Note, in general, the number of K permutations of a set of size n is what? Well, it's actually proved the exact same way. This formula is proved the exact same way as how we solved the last example, right? We would just list out k different slots here. In the example, k was 5, and then we'd start writing 52 times 51 times 50 and so on. Okay, as long as we had slots to fill. And then at the end, if we wanted to write it in this method, right, what would we get? Well, we would get 52 factorial on the top, right? And what would we have to divide by in order to actually obtain our correct answer? Well, what did we divide by in this case? Well, we used 5 slots here. Okay, so how many different slots would have been remaining to get to 52 factorial? Well, we saw it was 47, right? Well, 47, think about it, it's just 52 minus 5, right? We have 52 factorial, that's multiplying 52 numbers. Here, we multiply just the first 5. How many are remaining? Well, 52 minus 5. There's 47 left. And that would give us this 47 factorial on the bottom to cancel the 47 factorial we multiplied on the top to be able to write 52 factorial. So kind of extrapolating that pattern, feel free to go through it on your own, right? The same example, just in more generality, just list out k slots instead of just 5. Okay, but in the end, you're just going to get n factorial over n minus k factorial. Okay, so that's a really useful formula. It's going to come up a lot, and now we understand where it comes from, so we can feel free to use it. Okay, notice this also gets you for free the number of just permutations of a set, okay, which is what we did in our first example, right? Permutations of the elements of this set with 4 elements with just that size, 4 factorial. Well, remember, a k permutation, if we just take k equal to n, that's an n permutation. That was our definition just of a permutation. Right, permutation is the linear ordering of the elements of a set. A k permutation, if I just let k be the size of the set, is just a permutation of the elements in the set. So if I come down here and just let k equals n, I get n factorial divided by n minus n factorial, which is 0 factorial. Okay, and we have to know just that it's a fact of factorials. It was defined this way, that 0 factorial is not 0, it's actually 1. Okay, 0 factorial is 1. So that does come up, so you have to be aware of that. So n factorial divided by n minus n factorial at 0 factorial would just give you n factorial. So that's, in general, the number of permutations. Okay, so this formula works no matter what. And so that's what we got up here, right? The number of permutations of the elements of this set of size 4 was just 4 factorial. All right, good. So let's do another example. And this example is now going to lead us into our definition of combinations. Okay, so how many 5-card hands can be drawn from a deck of 52 cards. Okay, so what is a hand? Well, when you play like card games, a hand is just a set of cards that you're given. Okay, so you can rearrange them however you want. That doesn't change your hand. All that matters for a hand is which cards you have, which cards are in your hand. Okay, so let me just write that in case that's not familiar. So a hand is just a collection of cards, and that's in no particular order. Okay, we just care what cards are in your hand, literally in your hands. Okay, we don't care what order they are, we just care which cards are there. Okay, so we want to try and count this. We want to try and count how many 5-card hands can be drawn from a deck of 52 cards. Okay, how many ways are there to do this? And in order to count this, we're going to actually use our permutations. We're going to use the last example. So let's start with the 5 permutations. So this is where we do care about order. Right? This was like sequences of 5 cards that we could draw. Okay, we care what order we get them. And how many were there? This was our last example. We already figured this out. There were 52 factorial over 47 factorial. Right? That was our last example. Okay, but in this example, all we care about is which cards you have. We don't care about the order. So what we're going to do is we're going to take these 5 permutations and we're going to group them. We're going to put them all out on the table. There's lots of them. And then we're going to arrange them into piles, into these groups, okay, corresponding to which cards appear in that 5 permutation. Okay, so let me write that down. So now let's split these 5 permutations into groups based on which cards appear. Okay, so for instance, over here we have all the 5 permutations with the ace, 2, 3, 4, and 5 of hearts. Okay, so maybe I have 3 of hearts, 2 of hearts, ace of hearts, 4 of hearts, 5 of hearts. That's one 5 permutation. Maybe I have 5 of hearts, 4 of hearts, 3 of hearts, 2 of hearts, ace of hearts. That's another one. I'm going to put all of those into a group over here. All right, and then over here, maybe I have all the 5 permutations with the jack, queen, king of clubs, and the 4 and 7 of diamonds, right? Maybe all of those I put over on this side, right? They're all in a group because they all have the same 5 cards in them, just in all the different orders. And I'll just write dot, 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 etc. Okay, so I have all of these groups on the table, right? These are just 2 examples. I put all the 5 permutations on the table. I arrange them into groups depending on which cards appear in those permutations. And what we can notice here is that each group, right? Why is this helpful for counting our 5-card hands? Well, each group corresponds naturally to a particular 5-card hand. right? This would be the 5-card hand where we have those 5 cards. This would be the 5-card hand where we have those 5 cards, right? Each one of these groups, since I group them by which 5 cards appear in that 5 permutation, I can naturally have each of these groups correspond to a particular 5-card hand. Just say, all right, each 5-card hand corresponds to the group containing all the 5 permutations of those 5 cards. So if you think about it, our counting task at hand is to count how many 5-card hands there are, but based on this arrangement, based on this correspondence I've set up, okay, really all we want to count is how many groups there are. How many groups are there on this table? That'll give us how many 5-card hands there are. So let me write that. We want to count the number of groups. Okay, that's our goal. That'll give us exactly the number of 5-card hands. So how can we do that? How can we get the number of groups? Well, we know how many total 5 permutations there are. We already calculated that. Okay, now we split them all into groups. If it turns out that each group has the same number of cards in them, then if I take the total number, the same number of 5 permutations in them, if I take the total number of 5 permutations and I divide by the size of each group, I divide by how many 5 permutations are in each group, then I should end up with the number of groups, right? Because the number of groups times the size of each group, right? If they all happen to have the same size, which they will give me the total number of 5 permutations. So just sort of rearranging that equation, if I start with all the 5 permutations, divide by the size of each one of these groups, which will be the same number, okay, I'll get the total number of groups and we'll be done. Okay, so that's our question. How many 5 permutations are in each group? Okay, well, each group just has the same 5 cards rearranged in some way. So that's just the number of linear orderings of a set of size 5. The number of permutations of a set of size 5. And we know what that is. The number of linear orderings of a set of size 5, the number of permutations of a set of size 5, is just 5 factorial. We already did that. Okay, it's just 5 factorial. So each one of these groups has 5 factorial 5 permutations in them. Okay, so the number of 5-card hands, okay, which is just the number of groups, is, what did we say? Well, we wanted the total number of 5 permutations. That was everything we spread out on the table, all these 5 permutations. Then we want to divide by the size of each group. Okay? And that should give us the number of groups. That's what we wanted. And what is that? Well, the number of 5 permutations we saw was 52 factorial over 47 factorial. And the size of each group we just said was 5 factorial. And if I just rearrange this slightly, make it look a little nicer, 52 factorial over 5 factorial, 47 factorial. Okay, this is our answer. This is the number of 5-card hands, okay, we can draw from a deck. And it turns out this expression here comes up so frequently it gets special notation. Okay, so it turns out this is notated 52 and then a 5 on the bottom. Okay, and this is weird notation. We have parentheses, then we have 52 over 5. There's no line here, right? That would be a fraction. There's no line there. This is 52 with a 5 in parens. It's pronounced 52 choose 5. And let me just make our note here. Well, I guess it's sort of a definition. Okay, this notation, okay, which equals n factorial over k factorial times n minus k factorial. Okay, and it's pronounced n choose k. Okay, this is the number of subsets of size k that can be taken from a set of size n. Okay, that's the definition of this notation right here. Okay, it's the number of subsets of size k that can be taken from a set of size n. So in our problem, we wanted the number of 5 card hands. We didn't care about the order of cards within our hand. It was just about which set of 5 cards we have. Okay, if we wanted to count that, that's exactly this definition. That's exactly 52 choose 5, right? It's the number of subsets of 5 cards that you can take from the set of 52 cards in a deck. Okay, and this equation here is what we just walked through in this example, but of course it can be proved in the exact same way. It can be proved in the exact same way as the thought process we used in the example. Okay, so you can feel free to kind of think through that in more generality if you want, but you'll get the same result. Okay? All right. So these are what are sometimes called combinations, right? It's sort of like how many combinations of size k can you take from a set of size n. It's really just saying how many subsets of size k can you take from a set of size n. Okay, where the combination, different from permutation, right? With permutations, we cared about the order in which we listed the elements. Okay, but for this, for combinations, we only care about the set, okay, the set of elements. All right, so let's do an example. How many binary strings of length 10 contain at most 3 ones? Okay, how many binary strings of length 10 contain at most 3 ones? Okay, so we have, 10 slots here. Okay, and this would be a binary string. A binary string is just a string of zeros and ones, binary digits. Okay, so maybe the 3 ones could appear there. Okay, and in that case, the string has exactly 3 ones. Well, 3 is at most 3, so that we want to count that. Okay, or I could just have 2 ones, right? 2 is also at most 3. Okay, so I could have all the strings with 2 ones. Maybe they appear there, maybe they appear there, right, and so on. Right, so maybe these are, for example, just where my 3 ones appear. Okay, and we want to count how many binary strings contain at most 3 ones. Well, one way we can count that is to say, oh, the number of binary strings of length 10 with at most 3 ones, that's just the number of binary strings of length 10 with exactly 0 ones, or with exactly 1 1, or with exactly 2 ones, or with exactly 3 ones. Okay, so if we can count the number of binary strings of length 10 with exactly k ones, if we can count that, we can just add that number for k equals 0, 1, 2, and 3, and we'll have our answer. And of course, how many ones could we have in a binary string of length 10? We could have 0 ones all the way up to 10 ones. They could all be ones. Okay, so how can we count that? Well, if you think about it, I kind of have these locations mapped out, 1, 2, 3, all the way up to 10. I guess I'll just write them in. And if I want to count how many binary strings have, say, exactly 3 ones, well, if you think about it, that's the exact same counting problem as saying how many different subsets of size 3 can I take from a set of size n, right? Because in this case, the subset of size 3 would be the subset containing 1, 4, and 9, right? Or if maybe my 3 ones appeared here, here, and here, that would be the subset containing 5, 6, and 7. So you can see if I have a binary string that contains exactly 3 ones, okay, I could convert that to a subset of size 3 by just looking at where the ones appear. And conversely, if I gave you a subset of size 3, you could make a binary string with exactly 3 ones by just labeling the locations in that subset with a 1, and everything else is 0. Okay, so those two counting problems actually count the exact same thing, and so that falls exactly into our previous definition, okay, for our combinations there. This is just saying how many different subsets of size k are there from a set of size n. And that's just 10 choose k. Okay, n here is 10. Okay, so that's the number of binary strings with exactly k ones. And so our answer to our question is just 10 choose 0, that's the number of binary strings with 0 ones, plus 10 choose 1, plus 10 choose 2, plus 10 choose 3. Okay, so that's going to be 1. 10 choose 0 is just 1. How many different subsets of size 0 can I take from a set of size 10? Well, the only option is to take nothing. Okay, so there's only 1. But alternatively, you can of course plug in here. We'd have 10 factorial over 0 factorial, which remember we said was 1, divided by 10 minus 0 factorial. Well, that's just 10 factorial as well. So these two would cancel in that case. You just get 1. Plus 10 choose 1. How many ways are there to pick a subset of size 1? Well, we can just pick each of these subsets of size 1 once. How many are there? Well, there's 10 of them, right? I can just pick 1, I could pick 2, I could pick 3, and so on. So there's 10. Of course, you can plug into the formula and get that as well. 10 choose 2. What's that going to be? Well, that's going to be 10 factorial over 2 factorial times 10 minus 2 factorial. That's 8 factorial. And when I'm simplifying expressions like this, I always like to take the largest factorial in the denominator and cancel it with the top as much as possible. So 10 factorial over 8 factorial, kind of like when we were working with k permutations. 10 factorial over 8 factorial, well, 10 factorial is just 10 times 9 times 8 factorial. So those would cancel, and I'm just left with 10 times 9 over 2, because 2 factorial is just 2, 2 times 1. This is 10 times 9 over 2, plus 10 choose 3, that's going to be similar. Again, I want to cancel the 10 factorial with the larger factorial in the bottom, so I get 10 times 9 times 8 times 7 factorial, which cancels here, divided by 3 times 2. That's 3 factorial. So 10 times 9 times 8 over 3 times 2. Okay. All right, so what do I get? I get 1 plus 10 plus, well, 10 divided by 2 is 5, so 5 times 9 is 45, plus 9 divided by 3 is 3, 8 divided by 2 is 4, so I get 3 times 4, that's 12, times 10 is 120. Now if I add this up, I get 120 plus 45, that's 165, plus 10 is 175, plus 1 is 176. Okay, so that is the number of binary strings of length 10 with at most 3 ones. I would not recommend listing all of these out unless you really want to, but you can trust the math here. I mean, feel free if you really want. Okay, so that's good. All right, so that was an example, another example of using combinations where we don't care about the order in which things are listed. We just care about counting subsets, right? We just care about counting subsets. We want all of, in this case, thinking about the strings of length 10 with exactly k ones. We don't care what order the ones appear in our string. We just want to count how many different strings of length 10 contain exactly k ones somewhere. Exactly k ones somewhere. Okay, so we just care about subsets of size k taken from a set of size 10. Okay, for instance, if I had this example, right, I wouldn't care if you told me the locations of the ones. If you said, oh, it's 2, 5, 7, I wouldn't care if you said that, or if you said 5, 7, 2, right? I don't care what order you tell me the locations. I just care what subset of size 3 are you talking about. Oh, it's the set containing 2, 5, and 1, so I put 1s in those locations, and that gives me a binary string with exactly 3 ones. Okay? All right, good. So now let's do a final example where part of it we'll need to think about permutations, and part of it we'll need to think about combinations. Okay, so this will kind of hopefully solidify the difference between them, and you can see when you do future problems the kind of pattern of thinking you get in, and be able to identify, oh, that's counting permutations or that's counting combinations. Okay, so an ice cream shop has 10 flavors. Okay, a sundae consists of 3 distinct flavors in a bowl. Yeah, that's what a sundae is at this ice cream shop. How many ways are there to eat a distinct ice cream sundae each day for a week. Okay, so ice cream shop has 10 different flavors. A sundae is 3 flavors in a bowl. So what can we get from that description? Well, if I just give you 3 flavors in a bowl, is there any way to order them in a bowl? No, it's just 3 flavors in a bowl. We don't care in which way they're ordered. We just care which 3 flavors appear in the bowl. That gives us a distinct sundae. Okay, and the question is, how many ways are there to eat a distinct ice cream sundae each day for a week? Okay, so it's sort of like we're saying how many different schedules of eating a different ice cream sundae each day for a week, Monday, Tuesday, Wednesday, all the way to Sunday. How many different schedules of eating a different ice cream sundae each day for a week are possible? Okay, so let's take this in steps. First of all, let's try and figure out how many different sundaes there are. Well, there are how many different ice cream sundaes? Well, each sundae is pretty much just saying take a subset of size 3 from this set of size 10, the 10 different flavors. Any subset of size 3 gives us a different ice cream sundae. All the flavors just go in a bowl. Obviously, we don't care about which order. Okay, they're all just in the bowl together. Okay, so how many different sundaes are there? Well, since we don't care about the order in the bowl, we just care about the subset of size 3 of the flavors that are picked. That's just 10 choose 3. There are 10 choose 3 different sundaes. Okay, and now I want to think about my schedule. Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. Okay, so this is my schedule for eating these ice cream sundaes. Okay, and I'm just going to think about the number of options I have in each case. Well, on Monday, I can eat any one of the sundaes. There's 10 choose 3 of them. On Tuesday, right, I need to eat a distinct ice cream sundae each day for a week. On Tuesday, I can't eat the one that I just ate, so there's only 10 choose 3 minus 1 options for Tuesday. And for Wednesday, there's 10 choose 3 minus 2, and so on. Right, and so on. This is exactly the pattern of thinking we fell in when we were talking about permutations earlier. Okay, so what do we really want here? Well, we already figured out there's 10 choose 3 different sundaes. Now we want how many different orderings, right? Order matters, right? Eating some sundae on Monday and some other sundae on Tuesday is different than eating that other sundae I ate on Tuesday, actually eating it on Monday, and then eating the Monday sundae on Tuesday. Those are 2 different things. Those are 2 different schedules of eating ice cream sundaes on each day of the week. Okay, so order matters here. Okay, and that's the pattern of thinking we fell in. Okay, we didn't have to memorize anything. It just sort of appeared naturally in the problem. So what do we really want? We just want the number of 7 permutations, right? Because there's 7 days in a week. We want the number of 7 permutations, the number of ways of arranging 7 ice cream sundaes in a linear order for each day of the week. We want the number of 7 permutations of the set of all sundaes. And we already did the work. We already did the work to figure out how many there are. And we said there's 10 choose 3 factorial. Notice we're combining, right? 10 choose 3 notation, combination notation with permutation thinking here. Okay, so this is 10 choose 3 factorial over 10 choose 3 minus 7 factorial. Okay, this was what we saw. It was n factorial over n minus k factorial to count the number of k permutations of a set of size n. Okay, so that's exactly the pattern of thinking we fell in when we were doing this problem. Okay, so that's our answer. And of course, you could, get an actual number for that, but sometimes I prefer just leaving it in this notation because it's sort of more intuitive. It makes more sense how we got there than just seeing some final number. Okay, all right, so yeah, this last example, we used permutations and combinations, okay, in different places for obviously different reasons based on what the problem was asking. So hopefully all these examples have given you a good foundation for using permutations and combinations to solve future problems. All right, so that's all I had for this video. I'll see you in the next one.